Welcome to my talk about efficient task scheduling in a multi-threaded audio engine. Yes, I am Rachel, even though in the 90 minutes since I registered this morning, I seem to have already lost my badge. I'm a software engineer and a musician. And for those of you who were at Astrid's talk last year, yes, I am the Rachel who has more than 5 flutes. I've been working at Ableton since 2022, most recently on the real-time audio team for Live. And some of you may recognize me as one of the co-organizers of the Audio Developer Meetup in Berlin. Okay, so I already said the title of this talk is Efficient Task Scheduling in a Multi-Threaded Audio Engine. But let's break that down a bit to make sure we're all starting on the same page about what that actually means. So first, the audio engine. For our purposes, this is a software component in a DAW, though it can be in another audio application, which is responsible for things like reading input, rendering, or writing output, and for a whole bunch of other things too, like timing and synchronization, including latency compensation, triggering our processing units, and some would claim that DSP itself is also part of the engine, but sometimes it's considered a separate component, and also things like signal routing, automation, and mixing. So I also described this as a multi-threaded audio engine. Hopefully that's pretty self-explanatory. Most modern computers have multiple cores and allow multiple streams of work to progress simultaneously. Our audio engine wants to take advantage of this and parallelize its workload. I'm not going to go into details in this talk about atomics or synchronization, things like thread synchronization primitives or concurrent data management or lock-free algorithms, even though these are all closely related topics and will be mentioned in passing. Okay, so why do we care so much about being efficient? In audio, we're operating under real-time constraints with strict deadlines. So say some audio from a microphone gets written to our input buffer. Our application then processes that input and writes the resulting audio data to the output buffer. While that output is being played back, the application already needs to start processing the next buffer of input. If that processing takes too long, we miss the deadline and get a dropout. Since today we'll be talking about task scheduling, I should explain what a task is. For our purposes, this is one unit of work to be computed by a thread. That could be a single device like an instrument or audio effect, or multiple things can also be grouped together into a single task. A single device can also get broken into multiple discrete tasks. And this talk also doesn't cover how work gets divided into tasks, even though that breakdown can significantly impact how well a scheduler performs. So, speaking of schedulers, there are also a lot of things you can talk about when you talk about scheduling. There's CPU scheduling, so our OS decides when a processor thread can use the processor and for how long. There are all sorts of related topics, like setting thread priorities, differentiating between performance and efficiency cores, making use of OS-specific APIs like workgroups, and a whole bunch of other things. And these are all really interesting topics, but the one I'm going to talk about is known as job or task scheduling, which determines which threads compute which tasks and in what order. I'm not sure why. Oh, the audio is coming from the other room. Okay, I was about to say, I'm not even plugged in. There's something a bit odd going on now. It's coming through the wall. Why am I bringing you this topic today? A couple of years ago, clearly something going on this morning. A couple of years ago, it became clear at Ableton that our scheduler had become a performance bottleneck because it hadn't evolved sufficiently to meet the needs of today's music makers or modern hardware. We reap significant performance benefits by migrating from our legacy scheduler to one based on work stealing queues, which I'll describe later in this talk, assuming we do get our visuals back, but because it will be a bit tricky to do without visuals. Over the next half hour or so, I hope to demonstrate the impact that scheduling has on application performance, describe some classic approaches to scheduling in different contexts, and share real-world performance measurements. So we're done with the introduction. And our next order of business is to take a look at graphs and scheduling, after which we'll talk about scheduling for audio and some of the specific challenges that come up there. Then we'll look at some empirical data and discuss takeaways. This screenshot may look familiar to many of you. What we have here is a live set. So we have a bunch of tracks. They have instruments or effects, and we have MIDI and audio data that needs to get processed by these devices in a particular order, and then it gets passed on via track routings or sends, and finally output to the main track. And we can depict the dependencies that tell us in what order the processing needs to happen using a graph like this one here. For demonstration purposes, this example is greatly simplified compared to the actual live set in the previous slide. Here you can see the devices in each track, the sequence of data flow between devices, and finally the flow of data to the sends and the main out. Because they include the necessary information about data flow requirements, graphs are a really important data structure when it comes to task scheduling. A directed acyclic graph depicts which tasks must be completed before others, with an arrow pointing from predecessor to successor nodes. Each node can only be processed after all of its predecessors have completed execution. In an acyclic graph, no path will ever return to the same node. In audio apps where we do sometimes have cycles, we can break those cycles by inserting a buffer of latency, and then we can still depict the graph as acyclic. For our use case, each edge is given a weight based on the processing time of its source node. A path describes a sequence of steps through consecutive nodes in the graph, and the sum of the weights of the edges of that path is the total time that path takes. And all of the nodes in the graph must be processed once per buffer. Once we have our graph and the weights of the nodes, we can come up with a schedule. If we only have a single thread to work with, this is pretty simple. We perform what's known as a topological sort of the graph. If you're interested in how to implement this, there's a link at the end of the talk. Once this sorting is complete, we end up with a topological order, which is a sequential list of nodes where every node comes after its predecessors. A topological order of a graph is not unique. For example, after A has been scheduled, C could come before B in this example, and it would still be correct. Just a note, F is not included in this schedule because it has a processing time of 0, so that's why you don't see it up there. Now, you might be thinking, but Rachel, I thought we were talking about multi-threaded systems. Why are you showing me how to schedule on a single thread? Well, it starts to get a little more complicated. If you have enough threads to cover the maximum number of tasks that could be executing in parallel at any point in time, you can immediately assign each task to an available thread as soon as it becomes executable in what's known as a greedy algorithm. With these extra resources, we finish the work faster because, as you see here, B and C can run in parallel, as can D and E. For this graph, we can't get faster with more than 2 threads because B and C need to wait for A, and D and E can't execute until after C finishes. With a different topography, we can run even more tasks in parallel. So here, B, C, and D can all be executed after A completes. Although in this particular case, as we'll see in the next slide, we can be just as fast using only 2 threads. So if our number of threads is less than the maximum degree of parallelizability, if that's a word, at some point we have to choose which ready tasks to execute first. So here are 2 different possible schedules for this graph, Schedule A and Schedule B. Schedule B finishes executing the graph faster than Schedule A because it prioritizes task D, which is a longer running task, rather than starting with B and C. And because of that choice, both B and C can run on the second thread while D is still executing on the first. So that seems great, but what algorithm do we use to make sure we actually end up with the best schedule, given a weighted digraph as input and an arbitrary but finite number of threads? Unfortunately, this problem is NP-complete. So we would need to use brute force to find the optimal schedule, but there are algorithms for generating pretty good schedules. The papers I've read about doing this prioritize scheduling nodes that form part of the critical path. In this case, the critical path is the most expensive path through the graph, which here is highlighted in, I guess it looks gray up there, it's sort of purple on my screen, which is ADEF. And so when it comes to be time to decide when to schedule the other nodes, so the nodes that are not part of the critical path. So in Schedule B, that's, do we pick B or C to go first? Here, it doesn't matter, but in some cases, you can imagine that it might. Researchers recommend various approaches, and there are actually some cases where nodes like these would end up with higher priorities than a critical path node. For example, if a future critical path node depends on that non-critical path node, which I've heard called an interference node. Okay, with this in mind, we have everything we need now to implement task scheduling in our audio engine, right? Well, not quite. As we know, audio has some particular constraints. Not only do we need our scheduling algorithm to be really fast, since this is a real-time context, but we also don't really know how long a task is going to take to process until after we've already processed it. This value, which would give us the weight of an edge, can vary due to things like the arrival of MIDI notes or automation. And without this weight, we can't find the critical path through our graph. Enter the multiprocessor, multi-consumer queue, which can be thought of as the classic approach to dynamic scheduling in real-time contexts. Dynamic scheduling meaning we come up with our schedule on the fly, as opposed to static scheduling, which we saw before, where we were able to determine the schedule before we started executing any tasks. So how does that work? We start out with an unweighted graph this time, and here we have 2 threads, X and Y, which share a common lock-free queue. Thread X is awake and begins to execute the first task in the graph, task A. Once it's done with this task, both B and C are ready to execute. Thread X pushes both of these tasks onto the queue. It then wakes up thread Y, and both threads try to pop tasks from the queue. Unfortunately, that can result in contention if both threads are trying to pop at exactly the same time. Contention is simultaneous access to a shared resource that is being modified, and it can result in poor performance since only one of the contending threads can make progress at any point. I don't want to go too much into implementation details, since that would be a whole talk of its own. And if you are interested in these sorts of things, lock-free programming, memory ordering, etc., you should check out Timur's talk, which I think is later today. But I've included a simplified excerpt from the boost library implementation of the pop function that might look familiar to any of you who have dealt with lock-free algorithms. This code here is all inside of a loop and returns only once the compare exchange, which is updating the head pointer after copying the return value, succeeds. Or it also returns if the queue is empty, which I've left out for simplicity's sake. So yeah, contention is bad even in code where we're not using locks. So when we only have 2 threads, it's not so bad, but if a whole bunch of threads get woken up at once and all try to pop from the queue at the same time, we get what's called the thundering herd effect. And that effect is when many newly woken threads are all stuck looping around trying to succeed with that compare and swap. And in the meantime, cache lines keep getting invalidated when threads on other cores make progress, adding insult to injury and slowing us down further. But anyways, in our case, thread Y successfully pops task B and begins to execute it. Then thread X is free to pop task C. I'll go through the rest of this quickly since it's basically just more of the same. Thread Y finishes task B and goes to sleep since there are no other ready tasks. Thread X finishes C. It pushes D and E onto the queue. It then wakes Y. And we get that same situation that we had before. This time, X makes progress first, and Y ends up executing task E. Once we get to the end, Y doesn't bother pushing F onto the queue since it's the only remaining executable task. You might have caught that there's a small optimization we can use to reduce some of this contention. We start the same way with thread X executing task A, but when it's done, instead of pushing both B and C onto the queue, it reserves B for itself and only pushes C onto the queue. Then, once Y wakes up, it doesn't have to fight with X over who gets to push the next task from the queue. And so it's free to pop task C while X is already beginning to execute B, and we avoid the contention. This helps, but unfortunately it doesn't scale too well. So given this graph where we have 4 threads and threads W and X are currently executing tasks, when X finishes processing A, it reserves C and pushes D onto the queue. But then if thread Y, oh sorry, that was W, I called it X. So if thread Y, now we're on thread X. If thread X finishes task B, and it reserves E and pushes F, then once threads Y and Z wake up, we end up with the same situation we had before. Which brings us to work-stealing queues. The concept of work stealing has actually been around since the 1990s. Originally, it described how idle processors could steal threads from busy ones. The paper credited with inventing the work-stealing queue as a data structure was published back in 2005. So what is a work-stealing queue? It's a double-ended queue where each thread actually has its own queue, and instead of there being a single shared queue. The thread that owns a queue can push and pop from one end of the queue, and other threads can steal from the other end of the queue. To show what's so cool about work-stealing queues, I have to use a slightly more complicated example graph. Like before, thread X begins by executing task A. Once it's done, tasks B, C, and D are all ready to execute. the thread reserves task B and pushes C and D onto the queue that it owns. It then wakes up the other thread, and thread X can already start executing task B, while thread Y steals task D from X's queue and begins to execute it. Note that this means that popping has LIFO order and stealing has FIFO order. So once thread X finishes task B, now E and F are ready to execute, so the thread reserves task E and pushes F onto its queue. When it finishes E, it continues by popping F. And in the meantime, thread Y is finally finishing with task D. That took forever. So G, H, I, and J all become ready to execute. So Y reserves task G and pushes the remaining 3 tasks onto its queue. If right around now, thread X finishes with task F, and then with task C, and then around the same time, thread Y finishes processing G. Well, because pop and steal are working from opposite ends of the queue, we're able to avoid contention and both threads make progress. So now that we have a general idea of how these different approaches work, let's take a look at how well they perform in the real world. A bit about my testing setup. As you remember, we have to execute the entire graph every buffer. So all of these tests were run with very low latency, so about 333 microseconds per buffer. So any small inefficiency is really going to show up. Most of the tests were run on this MacBook Pro, which has 8 performance cores, and some additional testing was done with a Mac Studio that had twice the number of performance cores. We have done scheduler performance testing on Windows, don't worry. And we even added a Windows-specific optimization to our work stealing queue implementation that I don't really have time to get into today. But the specific tests I'll be sharing results from today were only run on Mac due to time constraints. There are 4 different scheduling algorithms I'm going to compare, not only 2. So the legacy schedule that you see here is the one that I mentioned toward the beginning of the talk that was causing us some issues. This is what shipped with Live in versions before Live 12, which was released last year. It was implemented in the early 2000s when multi-core development wasn't such a big thing. So just for a refresher, the first widely available dual-core consumer CPUs from Intel and AMD launched in 2005. NPM-C queues didn't become more widely used in high-performance systems until even later, sometime around 2010, 2015. Then the second scheduler I have there, Legacy 2.0, refers to an optimization I added when we were still testing the work stealing queues and weren't sure how long it would take to have that scheduler ready to ship. So we were considering making an incremental improvement instead, and that version never ended up shipping. Then, even though in Live we jumped straight from shipping the legacy scheduler to shipping work-stealing queues, because we already had a work-stealing queue implementation that we were using for a different use case, I didn't feel like this talk would be complete if I didn't compare their performance to NPM-C queues. And since Boost Lock-Free Queue gives us what we need here, it was actually pretty quick to swap in an NPM-C version of our scheduler to run tests on. Since I have included the legacy scheduler in these performance comparisons, here's just a really quick overview of that approach. That scheduler it had a constant vector of topologically sorted nodes, each of which has an atomic to represent its state, so whether it's ready to execute or already finished, and so on. There's also this other atomic, the effective start, which tells our scheduler where it should start looking for nodes that are ready to be executed. Since, as mentioned earlier, a topological order is not necessarily unique, the sorting of the nodes that was performed in advance in order to populate this vector might not actually result in the same order that occurs when scheduling dynamically. So the executable nodes might not all be consecutive the way they are in this diagram. Leaving out some small optimizations for the sake of simplicity, our scheduler basically just searched across this list of nodes, beginning with the effective start, and returned the next one that was ready to be executed. The Legacy 2.0 scheduler mostly keeps this approach intact, but it employs the optimization that we discussed earlier in the npm-cq example, where each thread reserves the task that it plans to work on before waking additional threads. The next slides are going to have a bunch of numbers, so I should explain what those numbers mean. As mentioned earlier, in real time, there's a deadline we have to meet. And this percentage over here on the right shows the amount of the allotted time that we used to do all of the work that we needed to do, which includes both the productive work, so actually processing the audio data, which is shown here by the task bubbles, and also any non-productive work, so scheduling and any other administrative tasks, and that's shown with the green bars. For any of you who are live users, this is the same value that shows up in the meter in the upper right-hand corner of your set. You can see here that these two schedules from an earlier example would show up as different values. Schedule A uses 95% of the allotted time, whereas Schedule B only used 85%, meaning that in the latter case, we could theoretically do 15% more work and not miss the deadline. So I really wish I could show you results that look like this. So across the board, we have significant improvements when switching to the work-stealing queues, and look at that. Like, our work-stealing queue scheduler doesn't slow down at all when we increase the number of threads. What? Or even better, in this fantasy world, when we double the number of cores, we actually finish things twice as fast. Have any of you ever actually had that happen? Any hands? No, no hands. Yeah, this is the real world. This is not an automobile emissions test. So the results I have to share with you are a bit messier. First, I forgot, that's the automobile emissions testing. So let's take a look at how the different schedulers performed on the MacBook Pro with a few different test cases. So in this chart, you see performance measurements from 5 different benchmarks. The empty set is just what it sounds like. It's that default live set that opens when you launch live and you don't add any of your own devices. Then second from the left is the demo set that ships with Live 12. And then the final 3 sets were designed to produce graphs that would try to pressure Live Scheduler in different ways. Interestingly, we can see that the legacy scheduler actually performs pretty well in those first 2 sets, but then it really starts to struggle once it's put under some pressure. In those later tests, we can also see how that task reservation optimization actually gave a really significant performance improvement in our Legacy 2.0. Then moving on to look at the npm-cq scheduler and the work-stealing queue approach, they appear to be pretty much neck and neck, though they definitely both outperform either of the versions of the legacy scheduler. Given this, I wanted to compare the performance of these schedulers across different core counts, since that's where the work-stealing queue approach is really expected to scale better. So I used an additional benchmarking set to really ramp up the pressure on the scheduler. Since I was mostly interested in comparing the MPMC and work-stealing queue schedulers with this test, I didn't try to prevent the worst-case scenario from missing the deadline, which was a consideration with the other benchmarks. The first thing you can see here is that both versions of the legacy scheduler missed the deadline quite dramatically on the machine with more cores. Those approaches clearly don't scale well to higher thread counts. And so both the MPMC and work-stealing queue schedulers far outperform the old approach. Let's take a closer look at them to compare them more directly. What we can see here is that the work-stealing queue does scale better than the MPMC to the higher thread count that we have on the Mac Studio. While the scheduler that uses an MPMC queue gives us about 15 percentage points worse performance when we double the thread count. With the work-stealing queue, we're only 13 percentage points worse on the Studio. We can imagine that this trend would continue with an even more powerful machine. I should note here that there are many other factors, not only the choice of data structure, that contribute to the poor scaling here, since we're benchmarking the whole system and not just running tests on the data structures in isolation. And that means that there are many other opportunities for optimizing this code, which are still being explored. I also want to note that these results don't mean that live is slower on a more powerful machine. In this set, even more than in any of the other benchmarks I shared, we're doing almost no productive work, just doing a whole lot of scheduling. With a real-world set, the speed-up achieved by the greater parallelization of productive work will almost always far outweigh any scheduler inefficiencies, even as we continue to work to reduce those. So, given these comparisons, it would be interesting to understand what actually contributes to lingering inefficiencies or where a particular scheduler's strengths lie. A scheduler might perform better because it produces a good schedule. So earlier, if you remember, we looked at how ordering the nodes differently on different threads can make one schedule faster than another. Or it could also have to do with how expensive it is to execute a particular algorithm, since those costs can slow things down, or the scheduler might run into contention, that sort of thing. And then finally, there are other factors like cache misses, destructive interference, that can have significant and often surprising impacts on performance. And these things are heavily influenced by which tasks are run on which threads and when. So if we want to look at the quality of a schedule, we can use what's called a make span. The make span measures the elapsed time from the beginning to the end of our graph execution. And so for our purposes, we're only including productive work in that, but still, of course, respecting all of the dependencies. To calculate the make span achieved by a dynamic scheduler, it's possible to use trace points to track how long each task takes to execute and which thread it was executed on. This data can then be combined with task dependency information as stored in the engine graph, and that can be used to reconstruct the schedule without including any of our overhead. The completion time, then, of the last active thread in this reconstruction gives us the make span. So here in this example, you see that even though we had two different schedules, we have the same make span because over here, D still needed to wait for B to complete before it could start. So with the same input that I was talking about, so that was these performance trace points, the graph information, et cetera, we can then use a static scheduling algorithm to come up with this pseudo-ideal schedule that we talked about in the first part of this talk. Then a comparison between that dynamic schedules, like the real schedule, and the post-facto generated static schedule makes it possible to quantify how good the dynamic scheduler's resulting schedule was. I don't think I've ever said the word schedule this many times in 40 minutes. It's all starting to sound the same: schedule, scheduler, scheduling. So yeah, our comparison between the ideal schedule and the real schedule can be represented by a ratio, which I refer to as the make-span ratio, and that gives us a ratio between the pseudo-ideal scheduler's make-span and the one from the real-world schedule. And then a second interesting metric we can use is what I refer to as the scheduling penalty. And this is different from scheduler overhead. The scheduler overhead is the percentage of on-CPU time not doing productive work, whereas the scheduling penalty only tells us how much that unproductive work actually slowed down our completion of processing, so not the total amount of time that was spent on unproductive work. To visualize that, both of these schedules here, so A and A prime, have the same scheduling penalty, even though A prime has a significant amount of additional scheduling overhead. And that overhead can matter for things like energy consumption and freeing computing resources for other running processes. But that additional overhead doesn't actually increase the amount of time it takes us to finish executing the buffer. I really wanted to be able to share some initial results today that would break out that analysis that I just described to you. But unfortunately, that work is still ongoing and wasn't ready to present. But I am really excited to see what we discover, because it will have an impact on the choices we make about where to optimize moving forward. So once we have that analysis, we can use that information to inform which optimizations will make a bigger performance difference and what the trade-offs are between different optimizations. So if our schedule isn't very good, we have a long make span relative to the ideal, then we can gain a lot by improving the schedule, whereas if it's the overhead that's really killing us, then that's the place to focus. So for future research, I also hope to improve some of the sets that we used for benchmarking, so they'll more specifically try to target particular pathological behaviors. You might also notice that the data I've shared only gives us the average load on our system, whereas in audio, we really care about worst-case scenarios. Analysis of peak loads is also still ongoing. We also want to continue comparing different hardware setups, especially given that it's no longer so unusual for a machine to have more than 16 cores. If we notice room for improvement in the quality of the schedule, it will be interesting to experiment with heuristics for the order in which we push tasks onto the queue instead of just doing it sort of randomly the way we do it now. And finally, there are other aspects of our system that haven't been updated to take advantage of modern hardware capabilities, which we can improve on as well with the help of additional performance profiling. Okay, that's been a lot of information. So it's time to wrap things up with a few takeaways. What this research shows, if nothing else, is that scheduling really matters, and that the schedule quality, overhead, and cache effects really all play a role. With detailed profiling and analysis, engineering resources can be focused on the areas that are most in need of improvement. Though work-stealing queues do scale better than MPMC queues at higher thread counts, work-stealing queues might not be worth the trouble yet. Unlike MPMC queues, it might be necessary to write your own implementation, and implementing them is difficult and error-prone. At this point, I'd probably recommend only migrating to work stealing queues if your scheduler is already pretty good and you've specifically identified the contention we discussed as causing a performance degradation. But on the bright side, since I found that it took actually less than an hour to replace work stealing queues with an MPMC queue in our scheduler implementation, I'm cautiously optimistic that inversely, a scheduler built around an MPMC queue could be fairly easily adapted for work stealing queues by just changing the underlying queue type and doing a few other things you need to do to make work stealing queues work. Then finally, we can see pretty clearly that some of the assumptions that are made at the time when a software product was developed no longer hold true as users and underlying technologies develop. So it's necessary to remain vigilant and to be willing to make changes when and where they're needed. I have a list of resources if you're interested in learning more about some of the topics I've covered. These slides will be posted online later so you can access all of this more easily. And that was it. Big thank you to Ryan for always being thorough in code reviews and for helping me with this talk, and also to Alex, Jeff, and Toby who gave me feedback on earlier versions of my slides. And with that, I'm not sure how much time we have for questions. Hopefully it's enough. OK, time for one question.